All right, that will greatly improve my ability to hold a mic. All right, so the title is Elasticity of Networks and Continuum Solids. And today we are going to focus on continuum solids. Tonight I will be giving a tutorial on Phoenix, which is an open source finite element platform, where we'll get to play around computationally with the topics I talk about today. I have a Google Colab notebook that I need to share with the class, so maybe the organizers can help me figure out how to distribute that. All right, so the references that I used in making these notes and that I recommend you look at for more. You may consider looking at Theory of Elasticity by Landau and Lifshitz. This is a classic. It is concise though. So it's nice to supplement it with some others. Another great book that I know many of us in this room are fond of is Elasticity and Geometry by Audely and Plummer. And especially chapter 1, I was able to take some nice examples from this book. Another excellent resource is Mathematics and Mechanics of Biological Growth. Mechanics of Biological Growth. This is relevant for obvious reasons to this workshop. Biological Growth by Gorley. And then a nice general resource if you have not seen this material in depth before. I like this book by Slaughter, The Linearized Theory of Elasticity, which in fact covers more than just the linearized theory, contrary to the name. So, who here is from a physics background? Mechanics? Who's taken a course on elasticity? Who has seen finite elasticity? All right, so we've got a range with some great background. So feel free to ask questions throughout. But I'm going to start with the basics. Good to know where you folks are coming from. So today I'm only going to be talking about continuum solids, and we're going to define a continuum solid as a collection of material points so that we can define fields, continuous fields on top of those material points. So displacement will be a continuous field, stiffness would be a continuous field, density, all of these things we're going to assume are continuous. And so we can say it's a space-filling collection of material points. Another way that this is often defined is that the smallest length scale relevant to the deformation itself is much larger than the microscopic length scale, the scale of an atom, something like this. And so we're concerned with the deformation of solid objects. And so a great way to frame our discussion is in terms of two configurations that we'll be referring to again and again throughout this lecture. So here is one configuration that I will define more about. And this configuration has a coordinate system associated with it. Then I will also draw a deformed configuration. Now I'm going to make a choice. I'm going to define a common origin. And now using this common origin, I can locate positions in these two configurations. Before I go any further, let me name these configurations. This configuration here is what we are going to call the reference configuration. This is what you can think of as before the deformation, although before in this case has no no notion of time. This is just what you might imagine prior to that happening. So if it's possible and convenient, we typically choose this to be a stress-free configuration, something in which the system is in its natural state and incurring no elastic cost. There are many cases, and many that we will actually, I believe, see over these 2 weeks, in which it's not possible or possibly not convenient to do that. Some examples that, well, actually, you'll see an example tonight as well. So some examples where you won't see that is if you had like a swelling inclusion. In this case, also buckling analyses are often done with the reference configuration, not necessarily stress-free. And we parameterize this reference configuration by tagging material points. Tagging material points. So let's do that. So I'm going to pick this point that I drew this arrow to, and I'm going to call it X. And that is going to be parameterized by coordinates x1, x2, and x3. So I'm using uppercase letters here. This is a common convention for the reference configuration to be described with capital letters. So that's the left-hand side of this. On the right-hand side, we have this actual configuration. So this is the configuration that we imagine really is existing. This is the deformation that we'd really like to understand something about. And it is going to be full of points that we can also tag. And here I'm going to use lowercase letters. I'm also going to give them a prime just because I don't trust my ability to differentiate between uppercase and lowercase x on a blackboard. So I'm sort of doubly tagging these points as in the actual configuration. All right, so this is our setup. This is really the charge that we have today, is to understand the difference between these two configurations. And the way in which we want to understand it is we want to assign an energy to this deformation. We want to assign an energy to the actual configuration. And the steps to doing that, there are two. The first step is we need to figure out how to describe this deformation mathematically. It's certainly much more complicated than something uniaxial. We're going to have to develop some machinery that allows us to quantify this. Describe the deformation mathematically. And this is going to give us strain tensors. And this is what I'll spend the majority of the talk on, because also I think it suits the school. This is where all the geometry is. We're putting this all into our strain tensor. This is the way that we're quantifying the geometry of deformation. And then the second thing that we need to do is, this is not just geometry of growth, it's geometry, mechanics, and physics of growth. So let's put in the mechanics. We are going to want to assign a cost to the strain. And I'm just using this strain. I'm using this a little colloquially. This is our strain energy functions. All right, so this is the goal of this lecture. But for those of you, which there are many of you, I learned, who have some background in elasticity, you might recognize this as kind of a narrow goal relative to the field of elasticity. There's a lot of things that we've left out. Something that is not, included in these goals, for example, would be the relationship between loadings and deformation, or the actual measure of internal forces within these objects. That would be the description of stress. That will be the loadings and deformations. So I'm not going to focus on stress today. That's just because of the limitation of time. And that will make this lecture somewhat limited in that there are a number of things in which you really need to work in terms of stress in order to understand, especially, well, let me instead say this. If you're someone with a background in elasticity, I encourage you to spend some time during this lecture thinking about what is left out if we're only working in terms of strain tensors and strain energy functions. What are the things that are it's not possible for us to describe if we are limiting ourselves in this way? And you might also say, this goal of assigning an energy to an actual configuration, there are many cases in which that's actually not our goal in elasticity. We want to understand something more about the dynamics. We want to understand something about a material in which energy does not fully describe the state of the system. And so this will be the goal for this lecture, but that's something we can discuss more about as well. What are other goals that lectures could have? So, all right, but this will be what we try to do today. So how should we start? This is where we're starting with this step 1, describing the deformation mathematically. So we are going to want to figure out a measure that is not just able to quantify the deformation, but is able to do it in a way that is reasonably efficient and easy for us to work with. And that is going to have some features. We want to figure out something that will be useful in our second goal, which is assigning a cost to this deformation. So in these simple settings, we don't want it to have any bearing on the cost of the deformations, what position the center of mass is in, right? We don't want rigid translations and rotations to have any impact on this. And so when we quantify the deformation, we're going to want to build up a quantity that is not going to be very sensitive to those details. That would be something that will simplify our life later on. And so to start, we're going to build a quantity called the displacement. The displacement is what you would intuitively think it is. It is the difference between the reference configuration and the actual configuration. And if I write this in terms of 3D elasticity, just so we have it, this will have 3 components. So here's our displacement. I'm choosing to write these displacements in terms of the reference configuration. And that's a choice I'm making. This is choosing to have these displacements be Lagrangian quantities so that we can imagine that what I'm doing is I'm drawing lines on this material before I deform them. And then those lines all have an identity that I'm able to track. This is in contrast to what we typically do in fluid mechanics, where we use what's called an Eulerian representation. So we have now expanding this definition out, again, emphasizing that we're using these reference coordinates to understand them. We can write out all 3. X1, X2. So now you see the difference between my capital and lowercase x's is getting increasingly subtle as this goes on. And now we have another tool that we're going to use. So we want to use this displacement to continue building some mathematical structure that's going to allow us to quantify this deformation. Okay, let me pause for a second. I've been talking for a while. Is anything unclear? Are there some questions at this stage? Yeah?
The reference configuration will always be Eulerian coordinate.
In this case, I'm defining a common origin for both of these, and I have these coordinate systems, and the reference configuration is determined in terms of this coordinate system. I'm not going to deal with something beyond that here. Yeah. Yeah. Oh, so maybe some of the other lecturers have a better response. What I've been doing so far is I've been using deformation as the thing that takes you from reference to actual. So more of this conceptual idea of this is the deformation, whereas the displacement is something that I'm giving an actual mathematical definition to. It is the actual difference between this. So I'm talking about the deformation as a sort of like general process, whereas the displacement is this field that I'm defining here. But yeah, I think that if you forced me to give you a definition for deformation, I would probably write down displacement. Great. All right, so let's figure out what to do with this quantity. What I'm going to do now is I'm going to pick another, well, let me actually put this in words so that you have it. I know I talk pretty fast, so I try and write down a skeleton of what I'm saying, so it slows me down. So we're going to consider the distance between two initially close points in the reference configuration, and we're going to see how that distance changes as we move to the actual configuration. So consider the distance between two initially close points. So let's draw that on the picture that we have. Have any other, these colors, I have plenty of colors. All right, so here's this other point. Put it over here. They're initially close together, and I'm going to define this other vector dx. Then over here, this point, so this is now the difference in position between this original point that I pointed out and this new point. And here on this one, we would expect both points to have moved. So maybe we're over here now, and this is dx prime. And now I'm going to draw some displacement vectors that will be useful to us. So here, between the first point that we tagged and the second point, we have u of x. And now we have also the distance between this new second point and this other point. And we have u of x plus dx. Again, I'm using this in terms of this reference configuration. And so now that I've defined those quantities, if what I want to do is consider the distance between two close points and how that distance changes, the mathematical quantity that I want to figure out is the difference between those two separation vectors. So this one is. So what is that equal to? We want to know what is going on with the length of this as it goes to here. At this point, we're not sure how complete of a picture of the deformation this will provide us with, but we can see it has a lot of appealing features. If I'm just considering distances, whatever I get out of this is not going to depend on rigid rotations and translations. It's going to automatically strip those out. So that will be a very nice feature. And so, hopefully this will be something that's useful to us if we're able to do it. So I'm going to calculate this, I'm going to do it in index notation. Who has seen index notation before? All right, pretty high, if not universal, yes there. So if you haven't seen it, it's summing over repeated indices. And we are going to first express our quantity dx prime so that we can make this more concise in terms of x and u. So let's start by building up some quantities that we might want to express. So here is our index notation version of the location of this deformed point. This, as we know from our definition of displacement, we can write it as xi plus ui, which is a function of this reference coordinate configuration. Then we also know that this new point, so all right, so what I just did is I said, this point can be written as taking the vector from here to here. And now I'm saying this new point is going to be able to be written as going from here to here and then over to here. So just vectors. So putting that in math, we have this plus ui x plus dx. And now this is our quantity that we are going to need in order to construct what we ultimately are looking to construct. So let's isolate that. We're going to move this over. We have xi minus xi prime dxi ui x plus dx. And now we can start recognizing things. This big xi minus xi prime, this is just minus the displacement at position x. And then what we can do is we can realize that we can Taylor expand this term. We can Taylor expand this term in order to simplify this expression, which will be nice because then we'll be able to have this in a more usable form. And the Taylor expansion that we're going to do in particular is x plus dx is approximately ui x plus partial ui partial xj dxj. And then now plugging this in, which is, again, you see very nice because we're going to have some nice cancellations. And we have dxi prime equal to dxi plus dui dxj dxj. Okay. This was all our prerequisite work. I haven't, this is to set us up for success in being able to write this down, but I haven't yet written this down yet. All I've done is figured out a nice way to represent dx prime in terms of quantities that are all nice and in terms of what we want them to be in terms of. And now here is our bringing it all together. We're now going to take this, and as you might anticipate, we're going to plug it in here. Then we already have d big X squared in terms of quantities of interest, and so we'll see some nice simplification. So writing this expression now in terms of indices, we have dxi prime minus dxk dxk, and this is going to be plugging in this quantity, partial ui partial xj dxj. So that's one of these dxi primes. Now let's put in the other dx prime. And again, you're already probably anticipating that we're going to see a nice cancellation here. And then we have these other indices that we're summing over, minus dxk dxk. All right, these terms, we now can FOIL this out. And we will do this. We have dxi, dxi. I'm going to actually just pull in this term now because we'll see these very nicely cancel. And then I'll take the cross term. Yeah. Oh, that was not the cross term. I was just writing another one. dxj, dxi plus ui, dxl, dxl, dxi. And now here's our cross term. dui, dxl, dxj, dxl. Okay. Hopefully I done all those right. These terms cancel. And now, because the summation is over both, well, over all the indices I've written, over I, j, and l, and because this quantity is nice and symmetric, we can rewrite it in a more concise form that I believe will start to look quite familiar. We have exj. And this is our first definition that we have gotten to. I'm going to call this quantity, which has two free indices, I and j. I'm going to call this epsilon ij. and pull out this dxi, dxj. And this epsilon ij is our green Lagrange strain tensor. Which is quite exciting. All right, I am now going to, for a page and a half, I have 4 kind of lengthy comments about this quantity that is also better expressed on this side. So again, let me pause and see any questions on what I've done so far. All right, let's see some comments. So comment 1. Actually, let me get a little more room for that. Comment 1. Features. So this strain tensor has some very desirable features. As I mentioned, as we motivated it, we don't have to worry about rigid translations or rotations. They don't enter because of how distance is defined. I think it's a nice intuitive reason why these don't enter. It's very clear from how we defined it that this is able to track changes in length. What is perhaps less obvious is that it also contains information about changes in angles. Contains info about changes in angles. If you are if you learned about strain first in an engineering context, you're used to treating these 2 types of deformation completely separately. But now we have the luxury of this single object that is able to contain both of those things. If you don't believe that, which I would encourage you to do this exercise suggested from Audley and Pomo, which is to consider 3 material points instead of just a pair of material points like we did for this definition. So you could call these points x, x plus dx1, and x plus dx2, and then their deformed image as well. And you can find out that dx1 prime dot dx2 prime minus dx1 prime dx2 prime. Oh, oops. These do not have primes. I was like, oh, that's 0. Okay, minus the reference configurator. So this is mimicking what we did over here, but now doing it in such a way that you're picking up these cosines, you're picking up these angles between these material points. We're making a material angle. Will give you, again, a quantity that can be expressed in terms of this green Lagrange strain tensor. So that's our comment 1. I think I have either 4 or 5, so. And each of these comments could be a whole lecture, or in one case, we'll see, more than a lecture. So this is, again, a lightning overview. Comment 2 is about compatibility. So what we have shown already is a prescription from going from displacements to strains. It's very clear that if you know everything about the displacement field, you know how to get the strains. A question we might want to ask is, especially in this context of the mechanics of growth, is what is it like if we want to do the opposite? What if we know the strains and you want to get the displacements? It turns out that you need to think a little bit harder in order to do that. So just writing what I said, it is clear. What's clear is going from displacements to strains. That's really what we just showed. But then what about strains to displacements? To do this, we need additional equations. And if you are not sure how to see this, one way to see this is that our strain tensor is symmetric. So the symmetric strain tensor in 3D has 6 independent components, while the displacement only has 3. So in order to go from strains to displacements, we need something called compatibility conditions. And I believe that compatibility equations, I believe that that is something that we will see this week in other forms, but that is all that I will say about it here. So comment 1, comment 2, comment 3 is about eigenvalues. Comment 3 is about eigenvalues. So what we built, epsilon ij, is, as I mentioned before, it's a real symmetric tensor. You can switch I and j, and that component will be the same. So if it is a real symmetric tensor, that is terrific news for us, because that means at every point it can be diagonalized. Maybe that's not clear yet why that's terrific news, but I will tell you. So it's a real symmetric tensor. It can be diagonalized at any point. Any point. So what that would look like is if you have epsilon ij, what you can do is you can find a coordinate system where the strain will look like this. And epsilon 1, epsilon 2, and epsilon 3 are called the principal strains. So this can be useful for a number of reasons. One reason this might be, well, the place that I see this show up the most in my research is actually when I'm trying to visualize a deformation. I think this can be a really powerful way to visualize a complex deformation. So what you can interpret this as saying is, if we go back to this picture of tagged material points. So these material points, you can think of them as tiny little spheres, right? And they're tiny little spheres, and this is just a packing of these tiny little spheres that then somehow get deformed. And all of these spheres will get deformed into these ellipsoids. And so let me say this differently. The fact that the spheres deform, and this tells us that since there's 3 principal strains where this deformation is diagonal, that's telling us that this can be deformed into an ellipsoid, where the change in length of the 3 axes of the ellipsoid correspond to these 3 principal strains. So this visualization of going from sphere to ellipsoid, it works for strain, it also works for stress. This can be a really nice way to think about what's going on, and to, you can actually start plotting these things as, in 2D an ellipse and 3D an ellipsoid. That can be a really powerful way to visualize things. This is also, of course, very useful if you're, a context you may have seen this in your engineering classes is when you're thinking about failure. If you have a material that fails at a critical strain or a critical elongation, as you might for especially a polymer network, you don't care about the strain in the X direction, the Y direction. What you care about is these principal strains, which will give you if you found the largest principal strain across the entire body, that would be the largest possible strain that you could have. So in some words. Strains give extension, these principal strains, not all strains. Principal strains give extension or compression along principal axes. So that takes a sphere to an ellipsoid. All right. So that's comment 3. And then my comment 4 is very long. This is where I want to tell you a little bit about how these ideas are used in finite elasticity and growth. And so, each of these would be multiple lectures in the elasticity class. This would be an entire semester. So again, I'm not doing any of these topics justice. Finite elasticity and growth. So typically we define strain. This way that I define the Green-Lagrange strain tensor. This is a classic way to derive strain if you are working, as your starting point for, if you're doing, eventually you want to linearize it. So, Slaughter does this, Landau and Lifshitz does it. It's also in Audely and Pommeau. If you eventually want to linearize it, or if you want to only consider what we'll call geometric nonlinearities, which I'm going to talk about, maybe that's comment 5. This will now go on forever. But if you ultimately are looking to consider a finite deformation, really sort of dramatic deformations, and especially growth, typically you get to the strain tensor by very different steps. So what are the steps that typically looks like? So words, strain is typically defined using different intermediate steps. When finite elasticity is the goal. Is the goal. So let's return to a previous step in our calculation. We are going to, we set this up nicely in order to allow us to do this calculation easily, but I'm going to bring us back to this step. So I'm going to say start here. So let's go back to that point, and let's rewrite it in a different way now. So I'm doing, you can see both of these boards at once. I need to rewrite this step for me. For me, that's a football field away. So here is that step. This is that tiny little distance between our two reference points that, again, we're assuming to be close together. Even though our goal is finite deformation, that doesn't change the assumption we're making that we're considering 2 points close together, because remember, we're trying to define these continuous fields on top of these continuous objects. That approximation is not going to be sacrificed. So what I can do here is I can recognize that I can actually pull out this reference length, dxi. So I can have this Kronecker delta. And I can rewrite this way. And then I see what I'm doing here is so I have a Kronecker delta, and then I still have the same dui dxj term, and then I've pulled out this dxj. And then I realize what is happening here is I have a 1 plus this little dui dxj, and I realize that that is something that I can now pull this derivative over to both sides, and I can write this as dxi prime dxj. times dxj. So what I've done here is I basically reversed that definition of the displacement from earlier. So nothing new here, just a manipulation. What this now does is it gives us this very interesting quantity here that we are going to focus on. But overall, what this step was always doing, and now we've rewritten it in a slightly different way, is we can think of this as defining a map that takes a line in the reference configuration, as we had there. It takes a line in the reference configuration. And moves it to the current moves it to the actual configuration. And the purpose of doing this rewriting is so that we write this map in a more concise form. And so we're going to call that map, we're going to call it Fij dxi dxj. And so I'm now sort of switching between communities, so I'm switching nomenclature. It's not typical to leave the primes on it when you're defining this in terms of this quantity, which is called the deformation gradient tensor. And now, since I'm not having the primes, it's more common to keep the indices capital or lowercase in order to emphasize that we're in the reference or the actual configuration. So this is a really interesting quantity. The deformation gradient tensor is a very general object. It's in fact more general than what we need for what I'm trying to show you today. It really allows you to not just have this common coordinate system here, this common origin, but it allows you to actually change the coordinate systems as you go from the reference to the deformed configuration. That's something that this object is sufficiently general to describe, but we are not going to explore that generality further. But you can see how it's baked in here as this very general map. All right, I have now exhausted my blackboard, so I'm going to do some erasing, which hopefully gives you time to catch up on my frantic writing, and I'll be happy to take some questions after I do that. Let me see what I want to keep and what I can sacrifice. I think almost everything. Yes.
Can you hear me?
Mm-hmm.
Yeah. So when you are doing the derivation, the dxi, dxj's, those product terms are not ordered, right?
They're not what?
They are not ordered in any way. So you can write dxi, dxj as dxj, dxi as well, right?
Yes.
So when you are relabeling after the second step of your derivation, you could have written it in a way that instead of getting a symmetrized del ui del xj plus del uj del xi, you could have gotten 2 times del ui del xj as well, right?
Yes.
But you have chosen to write it in a symmetric fashion.
Yes, so when I go, oh, you mean why am I writing these two like this?
Yes, that is not evident from the second step itself, right? That's a convention that you are choosing at that point, right?
Yes, because it's symmetric, I am allowed to, these are equivalent, and this is a form that's going to really emphasize the symmetry of this strain tensor. And I think because we use the symmetry of the strain tensor, it's nice to have it presented in this way.
But the symmetry of the strain tensor itself is an outcome of this in our derivation, right? We look at it and we call it symmetric. Or is this something externally imposed that you a priori think that the strain tensor has to be symmetric, and therefore this is a convenient way of writing it?
It has to be symmetric. So what you can do is you can look at all of these terms and you can see as I move the indices around, is anything changing? And because all of these indices are contracted with one another, all of those terms would not vary. It ends up just being shuffling around shuffling around these different indices. So it is symmetric because of the quantity that we're trying to find. It's symmetric because of this change in difference requires contracting all these indices, so you end up with this symmetric quantity. So there's no additional assumption or knowledge put in there. Thank you for the question. Okay, let me go back to erasing. Let's see if I can fill up all the boards a second time beforehand. Okay. So I probably shouldn't have erased that very last thing because we will build on it. We'll build on it now. So what do I want to bring from this? We had just defined our deformation gradient tensor. And there are many, many nice features of this object. One that I'll mention here is that if you are considering integrating over some volume in the actual configuration, and I'm not going to define everything very carefully just in the interest of time, but this is just a way of writing the integral over a small part of the actual configuration. This can be expressed as the determinant of this map over a little area in the reference configuration. And this quantity J, which is the determinant of F, has to be greater than 0. What does that mean? Well, this tells you that volume cannot be shrunk to a point. We're not going to allow ourselves in elasticity to annihilate volume. So this always has to be positive, which is very nice because it tells us that the inverse of the deformation gradient tensor exists, which is going to be something that is useful. So there are nice features of this quantity, but there are also features that are not so nice. One feature that is, I mean, maybe that's unfairly harsh to the deformation gradient tensor, but one thing that we're going to have to work a little harder to do is we're going to work a little harder to strip out those rigid translations and rotations. So this quantity is not something that is invariant under those transformations. If you were to impose, you can easily verify this yourself. If you were to impose rigid translation and rotation, this quantity would not read 0 as our green Lagrange strain tensor would have. So to remove rotations, translations are fine. To remove rotations from this quantity, because we're taking, the rigid translations would, of course, leave, rigid rotations would not. Quantity, it takes some work. Again, I won't present too much detail on this, but there is something very useful called the polar decomposition theorem, which allows us to write F as the product of the rotational part of the map times the rest of it, rotational part of map. So we can peel out those rigid rotations. And then we can also define another very useful quantity, C, which is something that you get from taking the transpose of the deformation gradient tensor times itself. That allows you to, the rotational part of the map will then give you unity, and you will get something that is the same as if you took this U and you squared it. This is something that you can also perhaps enjoy seeing in index notation instead, so that you can see again the usefulness of having capital and lowercase indices that allow you to talk about, is the map going from, having these lowercase and capital indices really emphasizes this is a map from the actual to reference and reference to actual, that they're going back and forth, and this can be written dxi, dxk, dxj. This is what this quantity C is in index notation. And I'm going to give this a name now. C is the right Cauchy-Green stretch tensor. Stretch tensor. And why did I introduce this quantity? Well, it will allow us to come full circle back to where we started, because our green Lagrange, I'm calling it our to give it a, I think that most of the speakers will be working in terms of this green Lagrange strain tensor. So I'm giving it a special status. So our green Lagrange strain tensor can be written in terms of this right Cauchy-Green stretch tensor. Can be written as epsilon is 1/2 C minus I, which is in indices dxk, dxi, dxk, dxj minus delta ij. Let me just add some primes here so that you know which is relevant. So now we are back full circle. We've shown that you can move between these two quantities, that the same information is contained in both. So if the same information is contained in both, why bother with this deformation gradient tensor? There are lots of good answers to that question. There are lots of advantages that this mathematical object has. The one that I will discuss here is the way in which the community has used the deformation gradient tensor to create a theory of morphoelasticity. The elasticity of growth is typically defined in terms of this object, this deformation gradient tensor. So here we go. In words, why introduce the deformation gradient tensor? And again, this is a narrow window onto a really rich field, and I really like the introduction provided by Slaughter to these topics. If you want to see a lot more and get some examples, Slaughter's book on the not so linearized theory of elasticity. So why introduce the deformation gradient tensor? For us, a compelling reason is that the kinematics of growth are often given in these terms. And this is often called the theory of morphoelasticity. And here is where we are moving to work that is described beautifully in this book by Gourley, introducing this theory of morphoelasticity. So Gourley and others working in morphoelasticity says, let's use this idea of thinking of maps between different configurations to describe this process of growth. So believe it or not, how I structured my notes, this is still technically comment 4. So I think I have a comment 5 after this. This is a long long side note on finite elasticity. So Gourley tells us that this is a nice way to think about growth in terms of these maps. So let's imagine a growth process that we can think of in 2 steps. So the first step would be a growth deformation. So we imagine a configuration that is some sort of reference configuration, just as we had before. And then we imagine, get one more color here, that every material point, again, think of these material points as these tiny little spheres. Every material point has, perhaps a mind of its own, perhaps just unique physical factors that are leading to it behaving in a certain way. So every material point grows some prescribed amount, regardless of any physical constraints. So there's some map that we can define where every material point grows a prescribed amount. And then what you have is some, actually, I want this to be the same approximate shape. Can I do it? Okay, so then what you might have is a mental picture of all of these deformed material points, maybe overlapping, maybe on top of each other, not necessarily looking like a continuous body, but we're just focusing on what these material points want to do. And this is sort of a classic figure to draw when introducing this idea. So if you want a more artistic version, I suggest you look at the books. So here, again, to emphasize, is a material element at its desired size and shape. And we call this state the virtual stress-free state. And we say that this map is given by a tensor G. So this is this growth deformation. And it's possible that these various little deformations are magically compatible, and that when every material point grows its desired amount, you get a state. If this state is stress-free and has no elastic cost, then the resulting state is also stress-free and has no elastic cost. An example of this would be if you just had every point double in size. Every point is just an isotropic expansion of the entire body. You would expect to have this be a compatible deformation. But it's also possible that this is not the case, that these points are going to grow in concert in such a controlled way that the resulting state is stress-free. Many of these, there are many beautiful examples. I think we'll see many of them, but one would just be a bilayer where one grows more than the other. You're going to have stresses develop, and in that case, you need to have a step 2. And in your step 2, you have an elastic deformation. Which is where you are forcing together these material elements that are all at their desired shape. You're saying, wait, we live in a world in which we expect this to still be a continuum. We're not allowing these material points to overlap. We need to jam them together somehow so that this is still an elastic body, even if that elastic body now has a non-zero or an increase in its elastic energy, let's say. So elastic deformation. So here, actually, let me try and take advantage of having already drawn this. So we'll say step 2, elastic deformation. And we are going to go from here And we are going to force material to restore compatibility. And this is going to give us some other configuration, which is our deformed actual configuration. And this map is given by a tensor that we'll call A. And then, according to this, theory of morphoelasticity, we can then assume that there is a multiplicative decomposition of the deformation gradient tensor. Such that F is equal to AG. And this is something that has been used heavily in the theory of growth. The work in the theory of, in this area, in this community, was really kickstarted by a paper by Rodriguez et al. In 1994, but actually this type of multiplicative decomposition has shown up in a number of communities very early on. Flory used this to understand polymer swelling in the 1950s, and it's also been used to understand defects and plasticity and thermoelasticity. So this is has broad applications, and you'll see it commonly. All right, so that is the extent of what I will say about finite elasticity and growth. My last comment on strain is going to be on linearization. Well, let me pause and take some questions. So comment 5 is on linearization. Is there a quick question on its morphoelasticity? Yeah. Yes, F is going to be something that is describing how it's describing the map from this reference configuration to the actual configuration. And so it has all the properties that we would expect. Yeah, yeah. Yeah, so I think so. I would have to think more about if there's any edge cases for these kind of things. But we're going to be, in the Phoenix tutorial, we're going to be doing one problem where we do a linearized growth problem, and we'll do one problem where we actually get to work with this formalism, and we can all apply a very, very nice choose your own growth tensors, so we can play around with that as well later on. Yeah. No. There's a lot more to say about a lot of things, but I want to, the thing that I'll give you a little preview. What I aspire to do versus what I'll be able to do may be different, but I want to show you the difference between a geometric nonlinearity and a material nonlinearity is what I want to introduce next. I want to do really surface level, what are some strain energy density functions? And then I have a page on stress tensors. Maybe I can start with the next lecture on it if other speakers haven't covered it by then. But again, I kind of decided early on that I would focus more on the geometry of this problem. Yeah. Yeah, so in this case, so there's a lot more to say about this, but in this case, what I'm imagining, the picture I'd like you to have is just something that doesn't fit together naturally. Like if you imagine the difference between something where everything swells isotropically so that there's no strain, there's no stress that's building up. There's no internal forces due to the growth versus a case in which there are internal forces generated due to the growth. And yeah, this is a much larger subject. So I'm just giving this like very glancing high level picture of it. But think of a case in which there is an elastic cost resulting from a growth deformation versus where there is no elastic cost. resulting from the growth deformation. Yeah. Yes, yes. No, 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 you don't need it. Mm-hmm. Mm-hmm. Yeah. Yes, yes, yes. There are lots of straight. Just because I'm not covering it doesn't mean it's not straightforward to cover. There are you can do this again as Suraj said, just purely geometrically thinking about, and incompatible elasticity is a really nice way of framing many conversations, especially in the theory of thin structures. But you can it is a yeah. Yes, there are many great answers to that question. Let me actually go a little bit further, and then I'll take a couple more questions. I want to make sure that I get to geometric nonlinearities before my time runs out. So, all right, so linearization. So why are we going to linearize? Maybe I don't need to convince you of this, but both formulations, this Cauchy Green-Lagrange strain tensor, as well as what we've developed with this deformation gradient tensor, both of them can be very challenging to work with. And in many cases, it's hard to get theoretical insight in all but very simple cases. So we want to figure out ways to simplify these strain tensors. And we maybe already have some sort of intuition that to simplify them, we need to somehow assume that the deformation is small. So somehow we want to do this. We may have this fuzzy idea that we want to simplify the strain under the condition that the deformation is small. But that's not really very precise. Small how? What does that mean? Are there different ways that this could be small? And the answer is yes, there are different ways that this could be small. So one option that we could have is that we could assume that actually let me write this down in coordinates so that we can play around with it a little more easily. Right, indices. So this is our xi. This is what you have in your notes. So one option is to assume that epsilon ij is small for all I and j, that actually the components of the strain tensor are small, which is that epsilon j is much, much less than 1 for all I and j. Intuitively, we can think of this as not much distortion. We could also assume something slightly different, which is that there are small slopes, small displacement, which we mean mathematically when we say this is this condition duk dxi, the magnitude of this is much, much less than 1. And both of these are dimensionless. And if this is true, then epsilon ij can be simplified to neglect this term quadratic in these slopes. This can be simplified so that this is 1/2 dui dxj plus duj dxi. So this is what's called our linearized strain tensor. And what I want to emphasize is that these are two quite different approximations, and the second is much stronger than the first. It is possible for you to have large slopes and small strains. And let me write this down. Two different approximations. And 2 is stronger. And so I think in the interest of time, I won't get to do this out, but I'm going to, there's an excellent example in Audley and Pommeau that I'm really fond of where you actually get a chance to see this. So I'm going to write down the map that you should do, and I really encourage you to try this yourself. I think it's a very nice example. Example demonstrating that it is possible to have one without two. So a nice way to do this is to consider a 3D material that is stretched along X and rotated an angle phi about Z. And so this map can be written in terms of X, Y, Z. Let me actually just write this in terms of X, Y, Z as lambda X cosine phi minus Y sine phi. Y prime X, Y, Z would be lambda X sine phi plus Y cosine phi. And Z prime would just be equal to Z. And when you do this, you can go through and you can calculate the linearized strain tensor and the Green-Lagrange strain tensor, and you find linearized. So what you find is that for the Green-Lagrange strain tensor, you have 1/2 lambda squared minus 1, and then the other components, are 0. And for linearized strain, you have a very different picture. You have this result. So what we learned from this is that if we're using this nonlinear strain tensor, as we anticipated, the rotations are dropping out. There's no mention of phi here, and this quantity is going to be small when lambda is approximately 1. If lambda is approximately 1, there's no stretching, but it doesn't matter how much you rotate this. This could be, spinning. But the linearized strain tensor, you're getting these terms that depend on phi, and those terms can actually be quite large. And so our takeaway here, is that even for a small stretch, which would be lambda approximately 1, you can't use the linear strain tensor if there is a possibility of large rotations. And this is what we call needing to include a geometric nonlinearity. And this appears often in slender structures. So an example where we can see this is if you just take a piece of paper on this desk, the reference coordination is going to have these, the coordinate system is going to align with the desk. And then if I bend it, I now have very large slopes relative to the desk, right? That's exactly what this term is. It's the slope relative to the desk. Very, very large slopes, but we're not having very large distortions of the material, right? We can assume that there's very little stretching. And so this is an example where you can think about this material rotating. You're getting these large slopes, and you need to include a geometric nonlinearity, or else you're getting, and this is something that really shows up quite a lot in computation as well. You can get results that look real, but you're using a completely wrong strain tensor, so they're picking up stresses that don't exist when you have these large deformations. Okay, so now I think I have just enough time to say the second part of what we set out to do here. So going way back to the beginning, what I said is I wanted to show, to give an overview of some of the different ways that we can quantitatively describe this deformation in terms of this reference and actual configuration. And then after I did that, I wanted to show you some ways that we actually write down the cost of that deformation. So we want to now create ways that we can write down the energy in terms of these quantities that we have gone to trouble to come up with. So recall our goal, which was number one, to describe the deformation mathematically. That's done. Well, I mean, it's a lifetime journey, but it's done for what I'll be showing you today. And number two is to figure out this cost. And this is something that we can do very generally if the strain tensor is small. So if the strain tensor is small in this sense, in the sense of number one, we can transform this question into the following, which is, so if strain tensor Eij is much less than 1, we can ask the question, what are the ways to make a scalar out of a symmetric second order tensor taking the lowest order? So when we do that, the answer is, this is our energy density. Energy density. And this gives us an expansion where we have a constant plus 1/2 lambda epsilon kk squared plus mu epsilon ij. And this is all there is at lowest order. This is all that we can do. Mu and lambda are the Lemay coefficients. And this factor of 1/2 is not required by the structure of tensors. It's by convention, and it's written this way to agree with a number of other definitions that I won't get a chance to introduce today. But this is an energy density, and this is the one that corresponds to linearized elasticity. So something that I have spent some time doing, and many people here spend some time doing, is thinking about elasticity in dimensions other than 3. And if you are doing that, this is the place to start, because this is a statement that doesn't depend on what dimension you're in. And so if you're trying to derive 2D elasticity, this is the place to start. And then you end up actually with, let me write these down. Let me write these down now. What you end up with is expressions for the Young's modulus and the Poisson's ratio, which you might be familiar with from linearized elasticity, that actually depend on the dimension. So I wanted to share these in case they are useful to folks, but the Lemay coefficients have units of energy density regardless of what dimension you're in, and so it's convenient to define these other quantities in terms of them. So you might see in the literature 2D Young's modulus, 2D Poisson's ratio. These are the ways that you would get these from this equation. And then the last thing I think I'll have time to tell you is, what do you do if the strain is not small? So I'm going to erase this panel, and I'm going I'm going to use what we derived just to its left. So just to its left, so we use the same approach if the strain is not small. What if the strain is not small? So then we need a different kind of nonlinearity called a material nonlinearity. We don't want a linear relationship between stress and strain, which then gives us this nice form of the energy density. So what we instead want to do is we need a material nonlinearity, which allows for large components of the strain. So we do this systematically using C. So what we will want to do to construct energy density functions is we can choose from a menu of invariants. Of C to build our strain energy function. So these might be the trace of C that we could call I1. They might be the trace of C squared minus the trace of C squared. Or we might have I3, which is the determinant of C. And these can all be written in terms of the eigenvalues very nicely. But I will just mention to close that there are a couple common choices that may come up later in the school or may not. One common choice would be a neo-Hookean energy. We would write this, the standard way to call a strain energy density functional in nonlinear elasticity is in terms of these W's. And this would be mu over 2 I1 minus 3. This would be for incompressible materials. In the Phoenix tutorial, we're going to work with the compressible version of the neo-Hookean strain energy density function. So this is used very commonly because it's the simplest model. Right? I think it's the simplest. I don't think that's too bold of a statement. This is the simplest model that has a material nonlinearity, but it struggles with large shear and large stretch in general. At large shear, et cetera. You don't want to apply this. This will be valid beyond what is possible for linearized strain, but it's not something you want to use for very, very dramatic deformations. If you want to go further, something like Mooney-Rivlin would be, one step up. Mathematically, this is third order elasticity instead of second order, like neo-Hookean is. And something like the Mooney-Rivlin strain energy density functional could be expressed in terms of more than just that first invariant. Could be also the second invariant. And then there are plenty of others. You might see Ogden, you might see Fung. Fung is particularly interesting for the purposes of biology because we can think of this as a generalized neo-Hookean that allows for strain hardening. So I think a good idea to have in your head is that Fung is usually good for biology. But there are plenty of others as well. Yes. You would, so yes. So if you were considering, there are a lot of materials that would be like it becomes a less accurate model in the same way that the linearized theory starts giving you strains that don't accurately reflect where the deformation is actually accurately penalizing these large deformations, and it doesn't reflect what we see in experiments. Yes, so Neo-Hookean is most accurately applied to rubber-like materials, but even in that case, for very, very large shear, you may want to move to something like Moody-Rivlin. So yes, so thank you for bearing with me for this really mad dash through elasticity. As anticipated, I did not get a chance to talk about stress. As I said, if it's not already covered, I'll do a really quick overview next time, but in short, stresses becomes more ambiguous to define because it's in terms of, it's a force per unit area, and what area to use becomes ambiguous. You have a lot of more choices to make that we didn't have to make for strain. And it becomes really interesting. In the next 2 lectures that I'll give, which will be on Thursday and Friday, I'm going to shift to focusing on polymer networks and polymer swelling and some discrete elasticity. So it'll be quite a different topic, and I will take it slower for them as well. But I really, thank you for your attention and going through it. And I'm around all week, so I'm happy to talk through any of these things with folks, and really looking forward to the rest of the school. So thank you. I went pretty significantly over, so I'm happy to take questions, or we can go to tea, and I can take questions there, whatever the organizers prefer. Okay, yeah. Oh, I saw this one first.
Minor point, but the I2, so does it have like one more trace than necessary? So.
Oh, did I miss? So let me write these in terms of how you most often see them. Yes, the second I2. On the outside that I don't need.
It's the sum, right?
This is in terms of the lambdas for F, not for C.
Right, okay.
And these are the more recognizable versions of them in terms of that. So these are in terms of the stretches, which are the eigenvalues of the deformation gradient tensor. Oh, yes. Because we assume that we don't need to, you can think of this as an expansion, and we don't have higher order terms.
So you just want to keep up to quadratic terms?
Yes, yeah, just the lowest order ways to create this quantity.
One could write down with C also, right? Without the linearized strain tensor. So then how do you differentiate between these two?
Yeah, you can, I'm not sure I'm completely getting your question, but what you could do is you can plug in this quantity into that expression. So this is exactly our Green-Lagrange strain, but the nonlinear version, and you could plug it into here, and you would get something that you can get something that in the small deformation regime looks like this. This term, we have mu and lambda here because this allows for finite compressibility, whereas I only wrote down Neo-Hookean for the incompressible case. There's more choices to make when you want to have a compressible Neo-Hookean model. Some people use different forms. We'll explore that a little bit in Phoenix. Allowing for that is important. Another way to see why this strain energy, this energy density fails is a way that some people say it is that there's only a finite cost to compress material to zero volume. So there's a finite energy that you could say, oh, look, I can destroy material. I only have to pay this much elastic energy. And that, of course, is not physical. Whereas these finite elasticity formulations, they will give you an infinite cost to bring a material, to take a large material and compress it down to a point. And that is something that you actually really do physically see in a finite element simulation. You'll literally see when you know that your linear linear version is failing, you'll actually see one of these triangles will just can go to a point, and you'll be like, oh wow, this really isn't the right energy functional. Yeah.
Given for the paper, so
Mhm.
depends.
Yes, great question. So I mostly will leave that to my colleagues. So everything I've done is bulk elasticity, and so in many cases you are happy to describe this as a bulk object until you actually want to say something useful about it, and then you want to have a dimensional reduction. And so in that case, you might think of the bending as being the result of a deformation across the thickness. So you can be stretching on the top and compressing on the bottom as you bend something. But the underpinnings of it are, in many cases, just elasticity. An interesting case in which it isn't is a material like graphene. A material like graphene that's purely two-dimensional, the actual physical origin of bending is different than the physical origin of stretching. So you think of stretching as the distance that the atoms want to be with each other, but they also have these orbitals out of plane that also don't want to overlap. So in certain cases, we often want to define a bending rigidity. I won't, I think I'll talk about that more on Thursday for discrete networks. And usually we can relate the bending rigidity to these elastic constants, but there are some cases in which that isn't actually responsible to do.
I have another question.
Sure.
So, so we talked about the compatibility, and then we said that to restore the compatibility, there is this elasticity that happens. So,
Mhm.
can there be other ways also to restore the compatibility? Like, for example, if the material points were independent, and so then there can be relative motion as well to restore the compatibility. Or, but
So you're talking a little bit about like viscoelasticity if you're allowing the material to flow as well.
yes.
Yeah, so there are a lot of very interesting things that cannot be expressed in just these elastic terms. And I think if some of you have been thinking about our bonus question of what do I lose for not having introduced strain in this or stress in this first lecture, I think being able to grapple with viscoelasticity is a great answer to that question. Yes, there are other ways. And then the other thing I wanted to say in response to your question, I think I may have forgotten the other thing I wanted to say in response to your question. You asked me, are there other ways? I just wanted to mention that when we're doing, I'm using this tutorial to extend the amount of time that I can subject you to this, but what you'll see is if you're trying to combine morphoelasticity and these functions, the quantity that we're actually going to put into get our right Cauchy green stress tensor is not actually going to be F, it's going to be A, because the elastic cost corresponds to that elastic deformation, that second step. It's not going to correspond. We don't want to include the growth in the function. In the same way that if you imagine like a marshmallow in the microwave, you don't want to just include the growth as something that's causing stress. Like it's not causing stress to blow something up isotropically. We only want to uncover what is actually going to incur an elastic cost. And so A is what's going to enter into these formulations when we're using morphoelasticity. Yeah. Yes, so often when we're working in elasticity in higher dimensions, we make a distinction between big D and little d. And I think we'll probably see more of this from other folks. This is very useful for slender structures where you might have the dimension of the elastic material and then also an embedding dimension. And so these both correspond to the dimension of the elastic material. So if this was graphene, this would be big D is equal to 2 and little d is equal to 3. And then if you solve through this, you would get the results that you would see quoted as 2D elastic constants. If you plug in big D is equal to 3, that would be bulk elasticity, and these should give you, if I wrote them down correctly, which I think I did, that will give you back your familiar equations that you would have for Young's modulus and Poisson's ratio. And you can do this for bulk modulus, you can do this exercise, but the point I wanted to emphasize here is that this is the place to start if you're doing those calculations. Yeah, thank you. Yeah. Mm-hmm. So I think I think there's a lot of choices that one can make about how do you relate this. I've introduced the growth tensor here as just this mathematical object that is just a map of what something exists and what it wants to grow into. Of course, when we're actually trying to make predictive models of growth, we want to tether that to something in physical reality, like maybe there are nutrients, maybe there is some sort of signaling, and then maybe you also want some sort of like constitutive law for growth where it's related to the amount of stress it's feeling and all of these other pictures. All of this is sort of assuming that you did that somewhere on the back end and then are just giving us what G is. And that might not be the right modeling choice for different contexts. And we'll do something a little more microscopic for swelling because we know more about what microscopically is going on with swelling of polymer networks. So we're able to. Great. All right. Thank you all.